Let's look at the logistic model. This is a treatment using calculus. You can say a lot about this with pre-calc, but we're going to really look at the calculus and differential equations viewpoint. So we have a function y of t, which is the population of something, fish in a pond, bacteria in a dish, people in a city. And the two assumptions that we're going to make, fundamental assumptions, is that when y is a small number, and we'll talk about that a little more explicitly in a second, then we're going to assume that we have the essentially the exponential model, roughly, and that's the relative growth rate, y prime over y, is approximately constant. And we're going to call that constant k, which would be, if this were exact for all y, we would get exponential growth. But we're going to assume also that the relative growth rate actually goes down to 0 as y approaches some number m, which we're going to call the carrying capacity. So the idea is that that's some limitation on the resources, perhaps, in the society, and that as you get close to the limit on resources, the relative rate of increase, maybe the birth rate, goes down, the death rate goes up. And we want to look at what the consequences of that are. Well, to make it more specific, we're going to look at the simplest model that would have that feature, and that's called the logistic model. And that's where the relative growth rate, y prime over y, is this constant, and then we're going to multiply it by a factor that when y is 0, it just gives you 1, so it returns to here. But as y increases and goes towards m, this extra factor goes down linearly, which is as simple as we can get, and then kills this, becomes 0 when y is exactly equal to m. So you can totally analyze this differential equation outside of the bounds 0 to m, but we're going to focus, and it just makes the math a little bit easier and focuses on this idea of growth, but constrained growth. And so a lot of the math works without that, but we're going to focus on that. So another way to say it a little bit more traditionally is to look at the absolute growth rate, just multiply by y. So that's usually known as the logistic differential equation. We'd like to solve that and show that it produces what you might have seen already, like in a pre-calc class, as the logistic model, which is based on exponentials but with some funky algebra. So let's first look. We really don't want to go to the algebra first. We want to first go to a slope field. So don't want to do this one by hand. You could. But here's the slope field. I've chosen k is 0.5 and m is 10. And I'm graphing mainly between 0 and 10. You can see that the slope field makes sense outside of that, but we're not going to focus on that. So what I want to do, I'm going to put in t equals 0 and y equals 5, halfway between the 0 and the carrying capacity. I'm going to have it plot an integral curve. And you notice that it looks very nice. It looks actually very symmetrical around that point. And in fact, we're going to discover that when we get the solution, it is exactly symmetrical around that point. But in fact, we can actually sort of justify that right now. The way these slopes work is that they are steepest in the middle. That's when both y and 1 minus y over m are relatively big. And they symmetrically get smaller as you go towards m and as you go towards 0. You can see that if we rewrite it in just a little bit of a different way. If you write this as k over m times y times m minus y. This is a factor that increases from 0 to m as y goes from 0 to m. This exactly symmetrically decreases from m to 0 as y goes from 0 to m. And so there's a lot of symmetry around the line y equals m over 2. And you can see that from this picture. So we could click on a bunch of random curves. And you might notice, at first maybe they'll look different. They have like different colors here. But if you actually look at each of those curves, they're all the same curve translated left to right. And we're going to discover that. And that's a very general feature, really. This is what's called an autonomous differential equation. dy dt does not explicitly depend on t. And anytime you have that feature, then the slope elements are the same as long as they're the same height, translate left to right. And the curves are all translates left to right of each other. So we really just have to find one curve and then slide it into the right place to match the initial condition. And I claim that this initial condition we started with, 0 and half of m, is a particularly nice one. So that's something we're going to be looking out for in the algebra. And in particular, it's going to, I'm going to look at what happens. I'm going to choose our initial condition to be exactly y equals m over 2 for a certain time, and that's going to produce the nicest form of the equation. And that's something that not a lot of books choose to do, but I think it's really a nice way to do it. So I'm going to go over to algebra here. Okay, here's our logistic equation. So let's do the algebra. We start out with this differential equation. And this is a classic example of a separable first order differential equation. We're going to combine the y stuff together. So I'm going to divide everything by y and 1 minus y over m. And then I'm going to integrate the left-hand side. The right-hand side, I'm going to multiply by dt to get the k and the dt together. That's easy to integrate, so I'll just do it right now. I get kt plus c. And of course, we're going to have to figure out the constant, and that's going to be something we're going to do something just a little bit clever. Now, on the left-hand side, you can do partial fractions. I'm not going to show that. It's a pretty darn easy case of partial fractions, but you can see the denominator factors into y and the 1 minus y over m. And when you do partial fractions, it's actually very pretty. It's just 1 over y plus 1 over m over 1 minus y over m. If you do you can always check that. If somebody shows you a partial fractions decomposition, checking it just means common denominator. Okay, and that's easy to integrate. 1 over y, of course, goes to ln y. And then this one's a little harder, but it's a very easy u sub, or you can check me. If you take the derivative of the log of 1 minus y over m, you'll get 1 over 1 minus y over m times a chain rule factor of minus 1 over m. We actually wanted the 1 over m, but we didn't want the minus sign, so that's why the minus is there. So I'm going through this kind of quickly. Okay, and no, you might notice I didn't put any absolute values here. That's because that's exactly one of the nice simplifications I get by only focusing on the case where y is between 0 and m. So both of these quantities are actually positive. If not, I'd have to do the absolute values and the plus or minuses later, and it's a little annoying. I don't want to avoid that. Okay, so now how do we solve something like that? This is a perfectly good equation relating y and t, but it's not y as a function of t, which is what we usually want. If you want to solve equations with logs and you've got the variable you want to solve for in 2 different logs, you better combine those using rules of logs. Well, we can do that. That's the natural log of the quotient. A difference of logs is a log of a quotient. Okay. And I'm going to go ahead and just multiply through by m, because I've got a compound fraction now. So I'm going to multiply through by m top and bottom. Pretty easy. Okay. So I would, it makes sense to just turn that natural log into an exponential, but I want to do something, this is where I want to do something a little bit clever. There's something a little bit weird about this quantity. If you look at like the units, say if y has units of like number of people or something like that, then we're taking the log here of something that would be like people squared over people, and we're taking the log of a quantity that has units, and that's a little suspicious. It's a little weird to take the log or the sine or the exponential or something like that that actually has honest units. And it turns out that things look very nice if we separate it out just by using rules of logs one more time into the log of something that doesn't have units. This would be people over people, dimensionless quantity, which makes more sense inside the log. And we've separated out this annoying log of some units part. And the great thing with logs and combining those with integrals is that when you have some annoying constant coming from a log and you have an arbitrary constant, I can just suck that into the arbitrary constant. So I'm just going to move that over. All I'm doing is I'm defining c prime to be c minus ln m, and it's gone. And that might seem a little bit like magic, but it happens a lot. This interplay with logs and constants. So this is going to be very pretty if we actually move the ln over into an exponential. But you know what? First, I'm going to go ahead and put in the initial condition. The quicker you can do that, as soon as you get to a place where you think it's going to be nice, the better. Don't put it in if you don't see a way it's going to be nice, but if you do see a way it's going to be nice, then put it in. So here's the initial condition I'm interested in. I'm going to look just at the case where y is halfway between the 0 and the carrying capacity, because we knew that was this sort of special symmetric point. It's in fact the inflection point of these curves, right? It's the inflection points of all these curves is y over 2. It's pretty clear from the picture. We could prove that later really carefully if we want. But I'm going to say what is the curve that goes through that special point at some arbitrary time t naught. because that's actually a very reasonable thing to look at. It's a meaningful thing to see in the picture. Oh, this blue curve is the one that goes through half of the carrying capacity when t is about minus 3.5. This yellow curve goes through half the carrying capacity. It's a very nice thing to eyeball when t is maybe 2.5. So that's the way I like to describe this, and it's a little bit different from, say, how Stewart does it. Okay, so we're going to put that in, and the great thing mathematically is that if y is m over 2, then you get m over 2 divided by m over 2 in the log. That's log of 1, and that's 0. That's a really nice thing when you're solving for a constant to get something equal to 0. So that's equal to kt naught plus c prime. So c prime is just minus kt naught. Or in other words, when we put it back in, kt minus kt naught is what we're getting on the right-hand side. That's just k times the quantity t minus t naught. That's a nice payoff. When you're solving a autonomous differential equation, you should be able to massage the constants so that it turns into just t minus t naught. Changing the t naught just slides it back and forth. We know that that's what we should be able to do. So that's part of the advantage here. And so what was that equal to? That was equal to log of y over m minus y. Now finally I turn it into an exponential. I just take the reciprocal of both sides and then realize that that turns into m over y minus y over y, or m over y minus 1. That reciprocal just changes the sign here. That's always a nice thing to do to an exponential. And then solving for y is just a couple more steps, and you get this, which is the logistic function, which again, you might well have seen before. A lot of pre-cal books, including ours, treat this, okay, as something you can do without calculus. Now, this might be a slightly different form from what you're expecting. In fact, it's a little bit different from Stewart. Stewart puts a constant here. I can't remember. He calls it a, I think. Instead of the t naught, he would take out the minus t naught. But I think that's a silly way to do things, because the t naught is something you can read off the equation. Remember the significance of the t naught. This curve, this particular logistic curve, goes through y equals m over 2 at t equals t naught. It was designed to do that. So that's the meaning. So m is the carrying capacity. K, remember, is a rate constant that's going to tell you what exponential does this look like in this zone down here where you haven't come near the carrying capacity. And t naught is simply when in time do you get to half the carrying capacity. So this is how I prefer to write the logistic function. So then you can do all the usual things you want to do with that. You can graph it, you can solve problems with it, you can set up plug in explicit numbers. But this is where I wanted to get to in this video.